get charged through the resistor. Because the resistance is a very high value, the charges will go very slowly. That means the potential difference. Hello. The purpose of this experiment is to investigate a capacitor resistor circuit. Now we have a 1000 microfarad capacitor. I have given you these values in the lab manual. Connected in series with the resistor, and then we will connect it in series with the battery so that the capacitor will get charged through the resistor. Because the resistance is a very high value, the charges will go very slowly. That means the potential difference across the capacitor will be increasing gradually, and we can take the measurements of the voltage. I want you to take measurements of the potential difference across the capacitor every 5 seconds for the first 1 minute, and then every 10 seconds for the next 2 minutes, and then every 20 seconds for the next 2 minutes. So altogether you take readings for about 5 minutes while the capacitor is getting charged. Now, if you remember, when a capacitor is getting charged, what is the relation between the potential difference across the capacitor at any time and the maximum potential difference? We have, let me write it over here. V at any time equal to Vf, which is the maximum potential difference, and that will be the EMF of the cell, times 1 minus e to the power negative t over tau. That is the expression we obtained in our theory. Now, if you haven't watched this lecture in the theory class, you are not really ready for this lab. So let me know if you are doing this lab, whether you have covered the theory part or not. Now, what is tau? Tau is the time constant, and it is equal to the resistance multiplied by the capacitor. That's the significance of that tau. So you will be taking the readings of the voltage across the capacitor. As I told you, for the first 1 minute, take the readings every 5 seconds, because the voltage readings will be increasing rapidly. And then it will slow down, so take the readings every 10 seconds for the next 2 minutes, and every 20 seconds the last 2 minutes. And you have a reading which will look like this. You have a time and the potential difference in volt. And how will the graph of this will look like? If you draw a graph of voltage against time, voltage against time, what happens as time increases? As time increases, this quantity will increase. That means 1 minus e to the negative t over tau will actually increase, because this quantity is going to decrease. E to the power of negative, a large quantity, will be very small. So 1 minus e to the power of negative tau will keep on increasing. So you have the graph going something like this, where it will asymptotically approach the maximum EMF, the maximum voltage, which is the EMF. So the graph will look like this. Now, what information can you obtain from this graph? Well, we should be able to measure the time constant from this graph. How? Well, let us say we have actually done this in the theory. If this time t is equal to tau, now suppose we said t equal to tau, what will this expression become? I'm going to write that over here using t equal to tau. Then I can write v equal to vf times 1 minus e to the power of negative tau over tau. So I replace that t with tau. And now this is e to the power of negative 1. And what is 1 minus e to the power of negative 1? You can calculate that. Use your calculator and find a value for that. What is 1 minus e to the power of negative 1? I think this will be approximately 0.63. So I will have then V equal to 0.63 Vf. In other words, this time t is such that during that time the voltage became 0.63 of the maximum voltage. Now, if the maximum voltage is the EMF and V equal to 0.6 Vf is say somewhere here, if this is 0.63 Vf, then draw a line to cut the graph over here and then measure the time corresponding to that, and that will be your tau. Alright, I'm going to explain that one more time. According to our definition, when this t equal to tau, then V equal to 0.63 Vf. In other words, this tau is the time taken for the voltage across the capacitor to become 0.63 of the maximum voltage, 0.63 of the EMF. If that is the EMF, then 0.63 of the EMF, from your graph, you can see where that exactly is. Draw a horizontal line to cut the graph, and then drop a line. That will give you the time corresponding to that. This will be your time constant. So obtain your time constant, and using that time constant value, I want you to obtain a value of the capacitor. Now, you know the actual value of the capacitor, that is 1000 microfarad, and that will be your calculated value. And you can now find a percent difference between the two. Well, for that you need the value of the resistor. And I'm going to give you the value of the resistor. Well, I want you to actually find that out. The resistor is color coded. And the color coding is actually given to you. The colors go like this. Let me write that here. It goes start right, black, brown, red, orange, yellow, green, blue, gray, white. Is that right? Let me see. Black is 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5. Well, this is so green, blue is 6, violet is 7, gray is 8, and white is 9. Now, how do we find the value of the resistor? Suppose you have something like this. You have a black to begin with. Well, black is 0. So, since I don't have many of the colors, I'm going to say you have a brown to begin with. Suppose the first color is brown, the second color is red, and the third color is blue. Now, write the number corresponding to brown. Brown is 1. And write the number corresponding to red. Red is 2. And then the third is blue, which is 6. And there are 6 zeros. That is how you read your register. So if the resistor reads brown, red, blue, it will be brown corresponds to 1, red correspond to 2, and blue correspond to 6. And the third color tells you how many zeros to add. So 1, 2, followed by 6 zeros. That resistor will be 12 million. Okay, I'm now going to show you that resistor. I want you to write down the value of the resistor right away. Okay? This is the circuit that we are using. We have the capacitor here, the resistor here. I have connected a cell, the battery, and you can see the charges will flow from the battery like this through the capacitor and through the resistor into the capacitor and out. That's the path of the charge. Well, I'm going to zoom in on the resistor. See if you can read the colors there. All right, give me a second. Well, I'm sure you can read those colors now. Now, the colors you are reading will be these 3 colors here. Now, let me point those out to you. First of all, well, it'll be that, and that. Those are the 3 colors. Now, forget about that. You're not including that in there. So your first color is this, second color is this, and the third color is that. Use those 3 colors and the color code I just gave you to calculate the value of this resistor. I have now connected the battery to the voltmeter, and this is therefore your EMF. So write down the EMF, that will be the maximum voltage. Alright, so you have now 2 important values that you need. You know the value of the resistor, and you know the maximum voltage V sub F. I have now connected the voltmeter across the capacitor, and the voltmeter will read when I turn the switch on. You're not ready yet. When I turn the switch on, this will read the voltmeter, the voltage across the capacitor. So what I want you to do now is to take your clock and keep it here, so that the clock will be here and you can refer the clock and the voltmeter side by side. So get your clock and keep it over here, and when I say ready, go, start the clock. Alright, I'm going to say ready, start your clock. Alright, ready, start your clock. it looks like you don't need to go any further. If you didn't get 5 minutes, that's okay. I think you have a sufficient spread of reading. You notice that in the beginning, the voltmeter was reading millivolts. That's about the first 1 second or so before it becomes 1, 2, and so on. So you got to be very careful. If you want to go back and do it again, try one more time. All right, now I'm going to discharge the capacitor. So this time you're going to take the readings while the capacitor is being discharged. All right, if you are ready with the clock, when I say go, start your time with 0. And I'm going to turn the switch to discharge. Ready, go. You can see now the readings are in millivolts. All right, I think that should be enough. Now, in this case, you got to take readings every 5 seconds because the discharge happened pretty fast. So you got to take every 5 seconds. All right, I'm going to stop now. How does the voltage change while the capacitor is discharged? Do you recognize that equation? Remember it? It will be V equal to Vf e to the power of negative t over tau. So, if you draw a graph of voltage against time, that will be an exponential decay. While charging, you get an exponential growth. While discharging, you get an exponential decay. And how do you find the value of tau in this case? Again, we set that time t equal to tau. When that t equal to tau, our equation becomes v equal to vf e to the power of negative tau over tau, which is e to the power of negative 1. And what is e to the power of negative 1? I think that will be 0.368. E to the power of negative 1 is 0.368 times Vf. So the time constant tau is the time taken for the voltage to fall to 0.368 of Vf. So you would come and say that's your Vf, which is your EMF, and where is 0.368 Vf? If it is somewhere here, draw a horizontal line to cut the graph and then bring it down and measure the time. That will be your tau. Now, so you get two values of tau, one while charging and the other while discharging. Take the average of the two and use that to obtain the value of the capacitor. So you know the value of the resistor, you can then obtain the value of the capacitor. Alright, I hope that lab is clear. Any questions, let me know.